Hi, nice to meet you. My name is Ivan, and I'm a postdoctoral researcher in the Mag Lab here working at Kansas State University.
Hi everyone, I'm Brian Spiesman. I'm an assistant professor here in entomology. I'm a pollinator ecologist and have worked a lot with Ivan on some of these issues in machine learning and artificial intelligence.
You can also download the dataset, you can scan the QR barcode, or you can follow the link in there. So this is an introductory course to do object detection on images. So the goal of this course is to be able to detect objects in the images. So you will have a data set of dandelions and also of coccinellids that is a natural predator. As an overview about what you will learn today is about machine learning. So machine learning is a very new topic right now that use automation. So you can automate a lot of agricultural tasks that you can be doing in the field, like sampling, that is very time consuming. For example, in my area, as entomologists, you need to count a lot of insects. So that is very time consuming. But with the use of machine learning, you can count automatically these objects on images. So as a general, machine learning in practice is just describing your data with features a computer can understand. And you will be building an algorithm that this algorithm will be able to detect objects on images. And we will be doing this with an open source software that is called Roboflow, that is pretty new. So you have common examples in machine learning. For example, you have Alexa. You can ask Alexa what is precision agriculture, and Alexa will provide you a response. Also, you have ChatGPT as a common examples, and also you have cars that can drive by themselves. So how it works, machine learning in general, you will be having some images that you already downloaded. And then we have to provide the computer a training data set. So the computer can be able to learn about the features that you are telling the computer. In this case, for example, we will be label these lady beetles in the images using a bounding box tool. A bounding box tool is just a predictor in machine learning that can help you locate the object in the image. Also, after you label all your training data set, then we will be applying a model that is built in Roboflow. So the model will be able to start mapping the pixels in the images, and then it will go through a process of training. We will learn how to train the model in Roboflow, and then the model will be able to map all the pixels in the images, and then it will go from this corner and start scanning all the pixels in the images. At the end of the training, you will have a model that will be able to detect objects in images that you didn't use for training. So that is the helpful about these things. So you train a model about a specific task, and then it will be able to infer in new images that the model didn't see before. So the first step about this workshop is to gather some data. We have some drones that we can fly outside if the weather permits. So you have different sensors right now that you can collect your data set. In our experience, we use different sensors. We use cameras. We have some GoPro cameras that you can use. You can use your cell phone. We created with Dr. McCornack an app that can detect aphids using images from your phone and can tell you how many they are. After, also you can use the drones to collect imagery. You can also import aerial imagery to Roboflow, and then you can create your detection model. Right now, currently, you have open source software that you can use to label your images. You can use Roboflow, and also you have another program that is called Labelbox. The beauty about these programs is that they are cloud-based, so everyone can access if they have internet connection, and also it has different capabilities of labeling and also different tools that you can use. Later, we will use Roboflow in this case to apply image analysis to resize your images, and we will use the open source Roboflow detection model that is built in the app. Also, if you want to expand these capabilities, you can train your own model. You will need to learn about coding Python. Also, you have Google Collaboratory. That is an infrastructure from Google that you can train any deep learning model using the computer infrastructure from Google. Instead of buying an expensive computer, you can just pay the subscription, and Google can help you to train your model. And it's faster and pretty straightforward. Also, you have some open source models that you can explore and apply to your own activities. You can enter the page of Ultralytics, that are the owners of the models that are called YOLO. So these models are very useful for detecting objects on images and are very easy to train and very fast. You also have PyTorch. At the end of the day, you want to have a model that works in images that the model never see it before. So right now we will train our model to be able to detect this tiny lady beetle. Also, you have a data set of dandelions, so you can detect the dandelions in flowers. As a workshop overview, I think that most of you download the data set. So you will have these two data sets. There are just 50 images, but with 50 images, you will be able to detect or train a learning model. If you want to increase the variability or something, we will have to collect more data set. So the model is more robust to make predictions in unseen images. We will learn how to label the images. So machine learning needs to be train the model, so you will be able to train the computer with the features that the computer can learn, and then it can infer. So you will be using a tool in the toolbox of Roboflow that is called bounding box. And then we have to go through each individual image, and then you have to draw a bounding box in the objects that we want to detect. In the case of the data set of the lady beetles, we'll be detecting, you have to draw a bounding box in the lady beetle, and in the case of dandelions, you will draw a bounding box in the dandelions. Also, you can detect these other flowers too. We didn't try that, but it's up to you if you want to. Also, you can upload your own data set and see if it works. Then we will train a deep learning model with the Roboflow model that is built in the software. And then we will test the model that you build in unseen images that the model never trained before. So there is the code for download the dataset, and please let us know if you have questions or if anyone has all the dataset in their computers. Cool. So then you need to log in your Roboflow account that I think that you previously created an account, right? So the Roboflow platform, it has their own model that we are not able to get the code of the model because it's a commercial company. But if you want to train your own deep learning model, you can just use Roboflow to label your images, and then you can use open source models and apply to your system. Then you will be able to have access to the code. But if you want to deploy your model, for example, into a web app, you can use the Google Cloud Console to deploy your model and create a web app. Also, you can use an application that is called Hugging Face, that you can upload your model, and then you can create a web app. Also, Roboflow has the capabilities to give you a type of prototype of a web interface to deploy your model so other users can use them. Also, it gives you an option to put to what is called this tiny computer. Is Raspberry Pi. Also, it has that option, Roboflow, that you can deploy the model to a Raspberry Pi that can be connected to a ground robotic vehicle and make real-time monitoring in the field. So we will go through that when you train your model. But that is the beauty about machine learning, that there has to be a way that the model will learn from images, and then you can retrain that model. So it continues building confidence for detection. In my experience, Roboflow is a good platform for labeling, for pre-processing imagery. But if you want to get the next step that Brian will talk about it, is about to get into like Python programming, use Google Colab, so then you can have more access to the code. Yes, you can get the APIs to connect to the Roboflow. but they will not give you like the code so you will be able to run in your own computer because it's for commercial use. So Roboflow also provides you some baseline code that is built with Google Colab. So you can use the URL or the API of Roboflow, and then it can extract your data set in Google Colab, and then you can train your model. But then you need to have access to Google Colab. Yes, it does. So when I started my PhD with Roboflow, we didn't have Roboflow 4 years ago. So I started doing machine learning with Python and with Anaconda libraries and connected with a GPU in the lab computer. So right now, this is, I believe that is a very big step because everything is connected right now and you don't need to have a computer that has to have like a huge GPU that are very expensive. You can upload any image size in Roboflow. Then in the same software, you can resize the image, and then it will be able to train your model. So there is a lot of pre-processing steps that you can do in the platform. It's not necessary to resize the image using other programs because everything is built in Roboflow right now. And the reason because we are doing that because the training will be faster instead of training an image that has so big dimensions. Right now, you don't have any deep learning model that can train that image size. It will take forever. You lose some information, but you can add more training data, so you have more variability. Also, the beauty about Roboflow that you can create augmentation, that is putting filters or putting some techniques in image analysis, so you can create different variability in your data set, so you will not be able to, the model will be able to learn about mistakes or filters that can happen. It will depend on the model that you want to train. So for example, the YOLO ones, the beauty about the YOLO models is that you can train from, I think that is from 225 pixels to 1,000 pixels. That is the range of the model. If you train your model more than that pixels, it will not run the model. So that is the beauty about YOLO that has different image. You can train your model at different image sizes.
Part of the augmentation process that Ivan was talking about is that, so if you do have a big 20 megapixel image, part of the augmentation process is that during each iteration of the training process, at training time, you can add in a process to take a smaller section of the image so that each time that, or each iteration through the training process, it sees like a different section of the image so that it doesn't look at the full image and sort of shrink the full image down to 480 by 480. It takes a section of it and shrinks that down so you're not losing so much information each step of the training process.
And it depends on the object that you can detect, that you want to detect, right? Like in our case, we are detecting insects. So for example, in aphid detection, we use something that is called mosaic augmentation that is built in Roboflow that creates creates an image with 4 different sections of an image, and you can have more variability to detect the aphids. So there is a lot of augmentation process that you can do in Roboflow without knowing all the coding behind. So it's just clicking a button and then it will augment your data. And then you skip this part because you don't have teammates, but usually you use this to engage with your labelers. So you can send to other people that help you labeling your images. Also Roboflow, right now they have a labeler team that can help you labeler, but you need to pay them. So then this is the interface that I believe you have right now. Okay, so right now you need to go and create a new project. So you will have this interface right now. Okay, so right now you can create you can put a name that you will remember for your project. Then this is the annotation group. The annotation group is the label that you put in the bounding box. So if you decide to do dandelions, you can put dandelions. If you like to do coccinellid, you can put coccinellid. But if you have your own data set, you can put, I don't know, any name that you want to label. Later on, you can also change the label of the bounding box. Then in this case, it will show you which task of machine learning you want to do. In this case, we are focused on object detection, but you can do classification, you can do segmentation, and key point detection that I never used this one before. But in this case, we will use object detection, okay? Then you will click in create a public project. You can do if you go to Google Colab and build your own model. So you can train for both. And Brian, in his B-machine algorithm, that's similar. Like I believe that is a classifier or a detection and then run a classifier. But Brian will go through that. You have that question. You can pay the private version, and it will keep you all your data set private for the users. But it costs a lot of money, but they have a discount for research purposes. So it's good to ask for the discount because it's pretty good. Then you create your public project, and you will have this screen, right? And then you will select a folder, and then you select the folder where is all your imagery. Yeah, the talent lios, you will have more to label, but that is cool, so you can practice. The coccinellid one just have one coccinellid in each image, I believe. Then the Roboflow will upload all your data set, and you can see all your imagery there. Then you will go to save and continue. That is in the bottom, in the upper right. Then in here, you have different options. So there is something that is called auto label. I can just explain. We will not use that part, but you can train a model with Roboflow, and then it will help you to label all your imagery based on the training. So you train your model with, I don't know, 50 images, but then your model can infer the labeling in any size of data set. So that is other cool thing. Because machine learning, I think that the most difficult part is to collect the data set and the labeling part. Then apply the deep learning models that are open source. It's pretty straightforward right now. Also, you can ask for Roboflow to label your images. You can contact them and see how it costs. I think that the Roboflow team, the price is like 3 cents per bounding box. And then we will start the manual labeling. So you can click and do the manual labeling. Then in here, you can also invite your teammates. So it can join with other teammates that can help you labeling your data set. But in this case, you will learn how to label all your 50 images. Then you will click in assign to myself, in your case. You will go and click start annotating. So in here, you have this is called the labeling tools from Roboflow. So you have a bounding box in here. That is the thing that you will use. Also, you have the segmentation tool that helps you segment things. So in this case, you can label the coccinellid, but also when you collect data set, you can label everything. So maybe in another type of project, you want to label the heads of the weed. Instead of going to the field and count the heads of the weed, you can train a model that can count heads of the weed and deploy to the drone, so the drone can be able to pick it up the heads. That can be helpful for GL purposes, for example. So in this case, you will use the bounding box tool, and then you will click in here, and then you will do the bounding box near to the edges of the lady beetle. And then you have to click enter. That is the label name that appears to you. And Roboflow will save all your imagery immediately.
Something also to consider while you're annotating is that the closer you can get the bounding box to the whatever you're looking at, the better. So you want your bounding box to really just like line up right to the very edge of your object. So the closer you can get to that, the more effective your model is going to be when you start training it.
You add your images, and then you go to generate. That is down there, generate, and then you will see this screen, and then you can resize your image. In this case, you will put 416 by 460. You will apply that, then you will hit continue. We will not use any augmentation, and then you will go to create, just follow the steps. Then the model will upload all your data set. And then you can choose what you want to do. So we will train with Roboflow. And then it will select a model that is pre-trained. And then you hit the start training. And then Roboflow will be doing your training. And then when everything is trained, you will receive an email from Roboflow that your model is trained, and you will see how the performance metrics of the model. You go to generate. You are here. So pre-processing, you can add the pre-processing step. And in here, you include resize, and then you change the number. For example, in here is 460 by 460. Then you apply. Then you click in continue. We will not use this part. But in here, just 1 minute, Barry. But in here, you have other type of image processing that you can use, and you can select what makes sense. And then you click in continue. Then you create. And then all the data set is uploaded. You go to train with Roboflow. You will select this is the commercial model of Roboflow. Then you hit continue. You can do accurate and fast, but for the purpose of the workshop, we will use fast training. And then you can use this standard setup that Roboflow already has. You will have a different screen because I already trained the model. And then you go and start training. Well, you just hit the start training, and then it will do it for you. Because I didn't change this part. It's different from you. And then Roboflow will send you an email and say, hey, your model is ready to go. Okay? Later, when you will receive your email, we will wait for that. And then Brian will talk about his research and other things that you can use with Roboflow.
One of the questions we had before was about image size and how that influences things. So one of the projects that we're starting this summer is using drones to go out and capture images of large areas so that we can primarily quantify the plant community. So my work is mainly in sort of natural systems, so like native prairies and grasslands, things like that. And so with pollinators, one of the things that's really challenging is because they forage over such large areas, one of the things that's challenging is to characterize the floral resources that they're actually utilizing. So we can go out with usually like a 1 meter square quadrat, put that down and manually figure out all of the different plant species that are in there. And then so you can imagine that this takes a long time if you're in a larger plot and you want to characterize the whole plant community. So one thing that we can do is fly drones out there and basically do object detection, kind of like we're doing, and then extract those objects and perform classification so that we can actually classify the species of plants that are out there. We can calculate flower area, so how much of the area of the grassland is actually in flower as a measure of floral resources. At the same time, we're going to capture bees that are foraging on plants. So there's kind of two stages to this. One is develop an object detection and classification model for the plant resources that are out there, the flowering resources. And the other is look at large-bodied bees that are actually foraging on some of these flowers too, so like bumblebees. So our project is focusing on bumblebees just because that's the sort of the low-hanging fruit with bees. I think we'll see how small we can get with some of the smaller bodied bees, but bumblebees are sort of the best bet right now. And so this is an image from a Mavic drone that we flew just a couple weeks ago, just to try to see what we can find when we put pinned bee specimens on here. So we put out 4 bees within each of these plots. This looks like it's out of the plot just because the plant is sort of tall, and it looks like it's just the angle of the drone. But so we have 4 different bee species. So these are 2. This is a queen of one species. That's a worker of the same species. And then this is a queen of a different species and a worker. So queens are always larger. So what we want to do is fly the drone at different altitudes using different cameras. So this particular drone had a zoom camera with a 7x. I think it's like a 166 millimeter lens, and we had a second camera that's sort of zooms out a little bit. It's a 3x, and then we had a wide. And so I'm just going to show some information from the 7x camera just because it provides sort of the best results here. So when we so I guess another step here also is, some of my previous work has been involved with building object detection algorithms and classification algorithms for bees. And so I have this a mobile app and website called Bee Machine, and the goal there is to basically classify all bee species in the world and have people be able to go out with their cell phone, take a picture of a bee, identify the species, and it gets uploaded to a database that will eventually serve as sort of a global scale citizen science data generation project. So with that, I've taken the bee detecting algorithm from that, as well as the bee classifier from that, and just applied it to some of this drone imagery. So I haven't done any training on this kind of imagery itself. I'm taking the algorithm, which has been trained in sort of a different context, but it still works here nevertheless, with a little bit of playing around with how we actually analyze the data. What I'm going to show here is kind of gets to your question before about how you take a large image that's this one's 12 megapixels, so it's 3,000 by 4,000 pixels. And then we're shrinking it down for input into the object detection algorithm to 480 by 480. So this is the relative change in size of the image. So you can see you're really losing a lot of information when you shrink it down. And so as a result, when you pass this through the object detection algorithm, it's only finding one of the 4 individuals here. One way to sort of address this and make this a little bit nicer is to break the image up into multiple smaller chunks. So you can take this image and make a grid out of it, and then apply one cell of the grid to the object detection algorithm at a time. And so when you take this full image and you take one cell out of a 6 by 8 grid and apply that to the algorithm each time. So then we're detecting all 4 species. We're also picking up something here, and it's so small. I'm not even actually sure what that is. I think it's a false positive. And so this kind of illustrates how this object detection algorithm wasn't trained on any of this. It wasn't trained on this kind of data. It wasn't trained on these kinds of images where the bees are so small. It was trained on images where the bees take up about that much space in the image, and so there's a lot of background noise here that the algorithm can pick up things that are sort of bee-like and still classify it as sort of classify it as a bee. I think with some additional training on this kind of imagery, we will be able to probably reduce the grid size, because once you start taking an image and chopping it up into smaller pieces, obviously it's going to take longer to process the full image. And so we're going to work on reducing this grid size by actually training the algorithm on these really small objects that we're seeing in here. And hopefully it'll start to get better. With overlap, so each of the, that's why it kind of looks weird. So so it's not taking like these tiny chunks here and these weird shapes. It's actually, there's overlap between each grid cell. And then when you reassemble the image, it'll take the largest. So if, for example, yeah, I'm not sure if this is would actually be cut, but if it was cut, it would take it would only be cut in one of the image. It wouldn't be cut in the other image that's overlapping that. So I think I had 40% overlap on these grid cells, and so when it reassembles the full image, it will take the largest object. And so this is something I haven't trained this yet. This is something that we're starting to do. What you guys did today is do the annotation. And so these are from a different image from that same data set where we went out and flew the drone around. These are small verbena flowers, and instead of drawing bounding boxes, we segmented the image. So we basically draw a little outline around each of the flower. This is some Joe Pye weed from a different data set, all labeled using Roboflow. And so we're going to be doing sort of similar things to what you guys did here with drawing bounding boxes and training object detection. We're going to try with segmentation, also with just using bounding boxes, and see what we get, see which kind of data set we get better results from. This is a little bit more data intensive. Obviously, it takes longer to draw the bounding or the segments here, but something that I started with Roboflow a while back and kind of haven't needed to actually use it in a while. And so when I opened it up just a couple weeks ago, I realized it has this really cool new feature where you can, instead of drawing a box, you could just tap on the flower and it will automatically draw this for you. So I think I saw that. I was wondering if that feature was available in the free version, and not? Okay. Yeah, and I'm not paying for it. I asked them a while back if I could have an educational discount, and they said, okay, yeah, you can just have the full version. So I don't know if they're still offering that, but I had to, there was no sort of box to check along the registration process. I had to email these folks and just ask them, and this was I don't know, maybe a year or two ago, and I'm not sure if they're so willing to do that anymore, but it's probably worth a try. But worth it if you have a team of people that can help you label. The free version only allows you to generate data sets of a certain size, so it's really limiting. You can't. It's not large enough to do full projects. You actually really need to pay for it. But there's other ways to do this if 250 is more than budgets can allow for. There's other methods, but Roboflow is kind of a very user-friendly. Yeah, and with this, it's drawing. So I annotated this whole image in, I don't know, like 5. I didn't time myself. It was like 5 or 10 minutes, using that sort of helper function where you can just tap on a flower. Sometimes it doesn't get it quite right, and so so for example, this one, I tapped on that one, and it probably included both of those. If that happens, then you could just tap on the one that you don't want, and it'll sort of shrink it back. It's pretty cool. And so I was able to go through this in about 5 or 10 minutes, whereas if I was drawing these by hand, I would still be working on it. Same thing with these smaller images. And what's cool is that each of these bounding boxes is a, so the sort of the unit of analysis in stats languages is not the image, it's the annotation. So this image has, probably, like 100 annotations which the algorithm can use it learns from each one of these. It doesn't just learn from the image, it learns from each of these annotations. So the same as this one. That's where we're going next. And so when we get the detector, the object detector sort of set up, then we can take that and extract. So if we know the species name of each of these flowers, then we can use this, extract each of these flowers, and use that as an image to start training a classification algorithm. And then hopefully, we'll see how well that goes. So there's you can start with sort of pre-trained models, which is what I have been doing. So we use EfficientNet, which is I found to be really good for training bee classifiers, but we're gonna explore a bunch of different ones. And so when I labeled it, I only labeled it as flower.
Oh, just flower?
Yeah, but that's for the object detection. So, but when I develop the classification model, then I'll relabel these by the species name, and so I'll have all of the species. You can actually do that with object detection too. So, for example, if each of these only has one species in it at once, but you could, instead of just labeling these flower, you could label it by the species name, and you could perform object detection and classification at the same time. I find that for classification, that's not, the models that are dedicated to classification work better than the models that are sort of perform both at once. And so I do it in two stages. I first detect it, crop it out automatically, send the cropped image to the classifier, and that tells me what species it is better than the object detection algorithm could. So that would involve some additional steps to it. One way is that if you extract this, if you know the size of a pixel in reality, like one pixel is like 2 millimeters or something like that, then you could just count pixels and multiply it by that. There's probably other ways. I haven't really thought about it yet. So especially if you're flying on a drone, the drone has all kinds of metadata in there that tells you how high you were flying, what camera you were using, the resolution of the camera, all that stuff. So you can calculate how large a pixel actually is on the ground. With just like a cell phone, you'd have to have some kind of scale bar in there to help you out, I think. So we have different ways to sort of evaluate how good your model is. So there's precision, recall. There's this average precision at 0.5. So basically different ways to say how good your model is. One of the things that we want to look at is how much overlap there is between the predicted box and the actual box that you drew. And so, for example, so this one, this map at 0.5, it basically it's a measure of what proportion of your boxes overlap with the actual or with the predicted box at 0.5. So if you have at least half of the predicted box overlapping with your drawn bounding box, well, that's considered a positive or a true positive. If it's less than 0.5, then that's considered a false negative. If there's no overlap at all, so you can get true positives, true negatives, false positives and false negatives, and so you can calculate all kinds of different metrics. So precision is when your model guesses how often. Yeah. So basically, how many times does it guess correctly? Recall is has your model guessed every time that it should have guessed? So basically, precision and recall are different ways of incorporating false positives and false negatives. So were these your results from the Cox and Nullid one? Okay. Mean average precision was 92.4. So that means of all of the bounding boxes that you drew, 92.4% were predicted accurately, or at least there was 50% overlap. And then you have other measures of precision and recall. That was for the coccinelle data set. For the dandelion data set, it looks like the scores were about the same. So I think about it in terms of classification. So when in classification, I haven't really thought about it in terms of the object detection, but in terms of classification, precision is if you don't know what the object is, it's how often it gives you the right answer. The recall is if you know what it is, how often does the prediction match? So it's basically different ways of incorporating true positives and false negatives. So it probably means it was guessing, you probably got some false positives in there, and that's why the recall went down. The precision was that you actually, of the things that were there, you actually got everything. So I think we'll be able to see examples of the predictions in the data set after the model is trained. So I think that's in there, right? All of the
You can see, yeah. Then Roboflow gives you like a platform that you can infer in unseen images. So you can run an image and then it will tell you where the beetle is located.
Different bits of information here. So you could tell your model, so okay, only show me the predictions where the confidence was 40% or greater. And so this is one of these things that when you actually apply your models, you really want to think about this in the end. So for the end user, if you lower your minimum confidence down, or if you increase your minimum confidence, you're going to only detect the things that you're looking for, but you run the risk of missing some detections. If you lower missing detections and getting false negatives, if you lower the minimum confidence, then you're going to pick up all of your, you'll reduce the risk of getting false negatives, but you'll increase the effect or the chances of getting a false positive. So detecting something that isn't actually the thing that you're looking for. And then overlap. So maximum overlap is when you have multiple objects in the same image. This will tell you, okay, so change how we determine what is a unique object. And so if the objects are really close together or actually overlapping, do we want to try to draw boxes around both of those things, or do we try to just get one of them, or just draw a box around both of them together? So it's how much overlap you have in the detection process. And yeah, and then you could just you could add your labels if you want. Just so if you have a multi-label algorithm, so you're trying to detect maybe two different kinds of flowers or bees and flowers at the same time, you could that will just turn that on, the name on and off.
Today you learn how to label and train a model with Roboflow. That is a very nice platform that at least gives you the hands-on experience of starting machine learning, because then you will not have to learn all the coding behind, but it's also important to know. And then you are able to detect objects in new images. That is the beauty of machine learning. And you can apply these tasks to different data sets with drone imagery, if you want to collect data sets with mobile phones or with GoPro cameras or anything. We are open to questions.